Okay, and let's go.
So these were just the examples that we had last time for you guys to finish up. Let's actually just knock them out really quickly. So we're going to use undetermined coefficients. So let's start with G. Okay, so remember, first step.
Homogeneous.
Homogeneous, how do you find it?
R squared minus 2r plus 1. R minus 1 squared.
So the homogeneous is?
C1 plus C2 e to the
It's all
Oh,
e
e
to
to the t.
all minus Okay. Next step.
Particular.
Alright, so we're going to choose yp. How is it chosen?
A, the polynomial is a second, so at squared plus bt plus c times e to the t. But now you have to look.
Yes, now you have to check, is there any overlaps? Well, c to the t is the same thing as c1 e to the t, so I can multiply by t.
C2.
Now, ct is overlapping with that one,
Square.
so multiply by t again. Now I have t squared e to the t, t cubed e to the t to the fourth e to the t. They're all linearly independent with that. So that would be my coefficients. So right now we're not worried about finding coefficients just yet. We just want to find, so the general solution would look like c1 e to the t plus c2 t e to the t plus a to the 4 plus bt cubed plus c2 squared e to the t. That would be our general solution. H. Okay, first thing,
R plus
we're
3.
going to find a homogeneous solution. What is that?
R plus 3, R minus 3.
R plus.
R plus 2, R minus 3.
So R to be minus 2, your R going to be 3. This means
C1 e to the negative 2t.
Y homogeneous is equal to C1 e to the minus 2x plus C2 e to the minus to the 3x. And so now, we want to choose a particular. So this is H continuing. How do we start by choosing?
0 degree polynomial, A.
So A times
Sine 3x plus B cosine 3x.
plus B. So once either a sine or a cosine shows up, you have to put a sum of both because they turn into each other when you're differentiating.
And then
First, right? So you know what's on yourself.
So now you check for any overlaps.
no.
No overlaps. So this means that's our general solution is going to have that form. Now you do need initial conditions to find the C1 and C2, as you should be aware. The A and the B, you don't actually need initial conditions. We can find them, but for now I just want to make sure that we can get to the form. We'll actually find the one in one of the last examples. So, let's see. I. What was I? Minus y prime minus 2y. What?
3x plus 4.
3x plus 4. Okay. R squared minus, so jump right into it. R squared minus 1 minus 2 equals 0. Does that factor? So our homogeneous C1 e to the 2x plus C2 e to the minus x. Our yp
AX plus 2. No overlap.
and no overlap. So our general solution that's that. Right into it, r squared plus 2r plus 3 equals 0. What is that?
Quadratic.
Huh?
Quadratic.
Right.
What's the quadratic formula?
So r is equal to?
Minus 2 plus or minus 4 minus 4 times 3. Divide by 2.
That is going to be minus 1 plus or minus.
2 square root 2 divide by 2 I.
Right, so radical 2 I. What does this mean for our homogeneous?
C1 e to the negative t cosine 2 square root 2 x plus c.
Any overlaps?
We haven't done a particular.
Overlaps?
What do you mean? You have to find the live peak.
Yeah.
Yeah, that's what's special, right?
What's it gonna look like?
A e to the x sine of x plus b e to the x sine of x. No overlap. We're
No
good.
overlaps. Okay. Trying to get into the gist of it. I don't know if any more examples here will be necessary, but we already wrote them down, so.
Why is it that the yp it has a cosine x and not squared x, cosine and sine squared x?
So it should be square root of 2 before the x in the bottom line.
In the bottom line, what about it?
Oh, because it's like cos of square root of 2x right above it, and then on the bottom you have a e to the x sine x.
Oh, because that's why H in the top.
Oh, this is YH, which is this, I just copied this.
Yeah.
And then YP, I put it in a second one.
But why is it that it's not sine, like a to e to the x sine the square of 2x?
Because it's g of t.
Why would it be? I mean, this is what it looks, we're trying to get it to look like.
Oh, okay.
There's no sine squared.
Right, thank you.
We want it to look like this, but not like that. So we first make it look like this. If it looks like that, we keep multiplying by t's until it doesn't look like that anymore. And why the sine squared? So r squared plus r plus 1 equals 0. What does that become?
Quadratic formula.
Minus b squared minus 4ac all over 2 So that's going to be minus 1/2 plus or minus radical 3 over 2 pi. So our homogeneous solution is going to look like C1 e to the minus x over 2 cosine radical 3 over 2x plus C2 e to the minus x over 2 sine of radical 3 over 2x. Okay, continue.
Half cosine.
All right, so how do we find yp?
Use the trigonometric identity.
Okay,
Half 1 minus cosine 2x. Or 1 plus.
so recall
1 minus cosine of 2x divided by 2. All of them divided by 2.
or 1 minus cosine 2x all over 2. Yes, you can write it as 1/2 minus 1/2 cosine 2x. And so what would you choose for your yp in this case?
A plus B cosine 2x plus C sine 2x.
Now, of course, there's a trick here. You should not assume that your yp looks something like a sine squared plus b cosine squared. That is not a good form. So you either have to write it as a sine or cosine without any powers, or use variation parameters. That would be the other option. Variation parameters can take that as is.
Could we still do it? Because if you differentiated that, all the answers are still in terms of sines and cosines. So it's a similar, self-similar. Because you could sort of, you could
That
only,
won't be self-similar to sine squared or cosine squared. Because I get sines times cosines. I wouldn't have like sum of sines and cosines. Right? Because I'd have to use the chain rule to differentiate. I would get sines and cosines. Okay. So that form isn't convenient. Technically, it works out as a sum of sines and cosines if we consider the double angles, not as is. So that would be what we would do here to get this to work. And so our general solution would look like C1 e to the minus x over 2 cosine radical 3 over 2x plus C2 e to the minus x over 2 sine radical 3 over 2x. Cosine 2x c x. And that is that. Now, we had a challenge problem. A fourth derivative. Now, we are going to deal with these guys in chapter 4, I want to say. They're in chapter 4. I kind of actually already did the theory for them, so there's not much to actually cover. Because when I was doing a lot of the things for the second one, I actually proved them in the nth order first. So y to the fourth, 8y to the y to the fourth derivative, 8y to the third derivative, t squared e to the minus 2. Minus cosine
start with 3.
So, as it turns out, the higher order linear differential equations with constant coefficients are actually dealt with in pretty much the same way as second order. So once you learn how to deal with second order, you kind of know how to deal with nth order, which is kind of why I sort of proved the theory for both of them at the same time. It's kind of like how Once you actually go to Calc 3 and you learn about vectors, you can do calculus in any number of dimensions after that, right? But just the jump from Calc 2 to Calc 3, that was a little crazy because we had to find a whole new way of thinking about the world because our functions, how we wrote them down, weren't good enough. Curves became 2D surfaces if we write them down the same way. So we had to figure out vectors and blah, 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 and then we could do calculus in any dimensions. The same holds true for differential equations. Once we figure out the second order case, the nth order case is extended naturally. So we would still, even though we wouldn't write it down, we would still assume your y is going to be some function of e to the rt, and you'll plug it in and you'll get a polynomial here. It's just that now the degree of the polynomial is going to be the same as the order of the differential equation. And so, ultimately, this is going to be, we're going to end up with a characteristic equation that looks like r to the 4th plus 8rt. And so now we're going to have to remember how to factor all that stuff. So you're going to have to remember all your long division, rational roots theorem, factor by grouping, all that stuff. We're all experts on it. That's child's play. All right, that's going to come back. That's going to be really make things a little bit more interesting. So, how would you actually solve that for R?
So instead of a matrix, combining.
Zero, so one of those, so I can say,
3 of them are 0.
yeah.
3 roots are 0, and the 4th root is -8. Yes, here complex solutions will be allowed, which means if you, whatever degree polynomial you write down, you must have that many roots, so you make sure you don't miss any. Let us, okay, so what would YH look like under these conditions?
C1 plus C2t plus C3t plus,
Squared.
oh yeah,
Plus C4,
e to the negative 3.
so that is our homogeneous. Huh? Yes, because this is the exponential. Okay, so now,
So you just keep adding t's basically, that's what it is, right?
yep, and we know we can do that by the reduction of order principle.
Yeah. Oh, okay.
So that's what we can do. We keep multiplying by t's to get new linearly independent solutions that behave similarly to some generating solution. Okay, so we have those, that's our homogeneous. Now we want to start with the particular.
AT squared plus BT.
Come in. This one? Where? Oh no, this e to the negative 2t is multiplied. Yeah. So now we are our yp, we need a polynomial. In fact, we need a second degree polynomial. We also need a constant times the e to the minus t. We also need, what else?
E to the negative 2t cosine square root 3t.
Yeah, cosine.
And then you need f.
Cosine 3t with the,
Okay, all that. Now we check for overlaps.
There, yeah.
This is actually so multiply by t. Any overlaps?
Yeah, CT.
Yeah, ct overlaps with that. So multiply by t again. Any overlaps?
Yeah, CT.
Yeah,
squared.
ct squared overlaps with that. So multiply by t again. So we actually multiply that by a t cubed to kill all overlaps. Any overlaps in the e to the minus 2t? No, that's e to the minus 8. And these guys are connected to the sines and cosines. So that's going to be your solution. So your y here is equal to that y8 plus the yp. So the biggest challenge here, since it seems that you guys are used to this part, is actually going to be solving the polynomials. You're going to have to remember how to do all these kinds of crazy factors. And I'm going to teach you a new way to factor things. Not factor things, to solve nth roots. Because that's actually going to be crazy. So because you look at something like r to the 4th equals 1. I mean, how many roots can you think about for that? Well, there's plus or minus 1.
yeah.
What are the other two?
You just multiply by p.
Right, I'm going to teach you how to find the other two. That's actually a whole lot of technique unto itself, which we're going to use Euler's equation to help us with. So that brings us with here. So all right, so now let's actually solve a problem. Let's actually solve a full problem. Here we were just kind of setting up the form of what the problem is going to look like, but let's actually solve one from start to finish so you can actually see everything that will go into it. We're even going to solve the C1s and the C2s because we were given initial conditions. So let's do that.
This took 20 minutes in his last lecture. In his video. He's a new and improved show. 2.0.
Get hydrated.
You didn't say we have these undetermined coefficients.
It'll be a while. Okay. You guys ready? It's too late. Okay. Okay, let's do it. First step. I want to find that hash.
R minus 2.
R minus 2 all squared. So we got 2, we have a repeated root of 2, so our homogeneous is going to be C1 e to the 2x plus C2
T.
well, I'm using x.
Sorry, yeah.
Yeah. But so we have that. Just multiply by x. That gets us the next solution. Yp.
Ax plus
Plus
b e to the 2x.
D.
E to the 2x.
Okay. Overlaps.
Yes.
Yes. Overlap here. And if we multiply by an x, we're going to overlap there. So we're going to multiply that by an x squared. So here is how we would actually find the coefficients. So you don't have to write this, but just so you're aware, since yp is a solution, it will solve the ODE. What that means, and we know what it means to solve the ODE, we spoke about that since lecture 1, means if you take this as a function and plug it into this, you will get that as the answer. So what I'm going to do is I'm going to look at the derivatives.
I have a
And-
question.
Yeah.
How do you know y of p solves the ODE?
What do you mean?
How do you know? Or what do we do to make sure, like, how do we know?
Well, we're using undetermined coefficients. So this just goes back to the theory. The assumption is to have a bunch of derivatives with constant coefficients all adding together to give us this thing. The function originally must have a very similar form to this thing. Namely, it must look like this. And that is the assumption. Because this is one of those nice forms. It's a polynomial and it's going to. So our yp is going to look like this, and we're going to assume this solves the differential equation. Now, if it solves the differential equation, it means that we can plug it in, and it will work. So we are going to have to find the derivatives. Yp prime is going to look like what?
2ax plus b
plus 2d. We have
product of
2d
x
x e to 2x.
2x.
2d x squared e to the 2x. Now do it again.
Now we're going to do that again. This part here, we can actually think of it as 2dx plus 2dx squared e to the 2x. So
Why don't you
we don't have
factor out
to do
an
the
x as
partial
well?
once. So this is going to be, there's differentiate this to 2a.
2a plus 2d e to the 2x plus 2x.
240x
2x.
plus 4 plus 3.
Okay. And we're going to yes?
You did the product rule over there?
Yes.
Okay.
So
Yeah.
you can double check. So I first factored out the e to the 2x, so it looks like the green. Then I differentiated the coefficient, which is just 2d plus 4dx, left the e to the 2x. Then differentiate the e to the 2x, which multiplies by the 2, the original coefficient stays, and I have the e to the 2x. So yeah, that's the product rule. Now, and that's why double. I'm not gonna use that board again, that's the last time I'm using this board. Okay, so. This is 3, continue. We are going to just plug it into that equation and see what the A, B, C, D needs to be to solve that equation. So, this means we are going to have 2a plus 2b plus 4dx plus 4dx plus 4dx squared e to the 2x, and that's my y double prime, minus 4 times the y prime. So that's going to be minus 8ax minus 4b minus 8d minus 4, so that's going to be minus 8 dx e to the 2x minus 8 dx squared e to the 2x. That is my y prime. Now I'm going to take 4 times the y. Where's the y? Over there. Okay.
Yeah.
So 4ax squared plus 4bx plus 4c plus 4bx squared e to the 2x. And all of this, by the way, is going to be equal to x squared plus 12 e to the 2x. Now let's look at what the left side is going to simplify to. Alright, so let's do one thing at a time. Let's look at all the x squares. Group all the x squares. You board them like the classes on a flight. How many x squares do we have?
Minus 8d e to the 2x.
2, 4, 4.
This one. 4a.
4b. At the end,
4dx squared e to
the
the
last one?
What last one?
4dx squared. 4dx squared?
That's not a 4dx squared. That's a 4dx squared e to the 2x. These are all the x squares there.
What?
How many x's are there? Call in all the x's.
Minus 8a.
Here are 2 x's right here. So at 8d, those are the x's.
Isn't that an e to x?
Minus,
Yeah, it's an e to the 2x.
oh, there's one up there. You have to worry about.
Oh,
You don't want the x's multiplied by any of the exponentials. You consider those as separate things.
there's only minus
So
8.
minus 8a,
Minus 8a,
then 4b plus
Plus
4b.
4b.
4b from here. Those are all the x's. All the constants.
4c and 2a.
We'll have 2a. Give me this guy here.
Oh yeah, negative
Minus
4c.
4b.
Minus 4b
Plus 4c.
plus 4c. That's it. So, plus. Now let's, what? Yes, the e to the 2x stuff. We also want the x e to the 2x 2x stuff. We also want the x squared e to the 2x stuff. And I think that'll cover all the stuff.
Yeah.
Okay.
That's no
So the e to the 2x stuff, only things that are a constant times e to the 2x.
So 2D.
So the 2d,
2D plus 8D.
That's it?
Plus 8dx.
No,
No.
because that's X.
Oh, that's technically an x.
okay, so that's all, that's all, right?
Yeah.
Now the x e to the 2x, if I were to multiply out to get x e to the 2x, 8d
Oh, that's no.
Minus 8d.
Minus 8D.
minus 8d,
Okay. That's it.
that's it. And then for the x squares,
4D plus 4D.
4d x squared plus 4d x squared, so that's 8dx squared
Minus 8D.
Minus 8d.
minus 8d x squared.
Nice.
Okay, that accounts for everybody. Okay, so now these guys actually go to 0, so I don't have to worry about them. And now what you do is you equate coefficients. So the number of x squares on this side must be equal to the number of x squares on that side.
Wait, Professor?
Yes.
So if they didn't go to 0, so you would just write that thing equals to
If it didn't go to 0, I'll just leave them like what I have here. And I'll
No, you would
write
just
this.
equal to, yeah, if everything else is the same and they didn't equal to 0, you would just set that
The
thing.
coefficients would be 0.
Wait, what?
We're equating coefficients. That's what we're going to do.
Yeah, you're basically taking each part from the right side and equating.
Yes. Each thing from the on the left and the right should be the same. So the number of x squares I have on this side must be the number of x squares I have on that side. I have 1 x squared on this side, which means the 1 must be equal to 4a. So now I've accounted for that coefficient. Now the number of x's on that side must be the number of x's on this side. How many x's do I have on that side? I have 0 x's on that side, which means 0 should be equal to minus 8a plus 4b. That accounts for this. Now the constant term on that side must be the constant term on this side, which means 0, because there's 0 constant term here, must be equal to 2a minus 4b plus 4c. That accounts for this. Now the number of e to the 2 x's on that side must be the number of e to the 2 x's on this side, which means that 12 is going to be equal to 2e. So now you realize I have 4 equations and 4 unknowns. I can solve this. So what do we have? We have here a is equal to 1 over 4. We also have that d is equal to 6. Since a is equal to 1 over 4, this means that 0 is equal to minus 8 times 1 over 4 plus 4b. So this means that 0 is equal to minus 2 plus 4b. So this means my b is equal to 1/2. And then I have this 0 is equal to 2 times the a minus 4 times the b plus 4 times the c. So this means that 0 is equal to 1/2 minus 2 plus 4c. 0 is equal to, that's 1 over 2 minus 4 over 2 minus 3 over 2 plus 4c. So this means that c is equal to 3 over 8. Right? So, yeah, so those are all my coefficients. So now I actually found the actual coefficients for y. So now my y general solution.
Oh no, we're supposed to do something.
Here's it's
C1
going to
and
look
C2.
like.
Yeah.
Where's the other guy? Where did I put it? Okay, here it is. Okay, so A times x squared, my A was a quarter, 1/4 x squared plus B 1/2 x plus C 3/8 plus D 6x squared e to the 2x plus the homogeneous solution, which was just a repeated root at 2 plus C1 e to the 2x plus C2x e to the 2x. That is my general solution. But we're not done. Now we need C1 and C2s. So, now what we're going to do is
Y of 0 is
our y prime would be what?
2 over 4x plus x plus 12x e to the 2x plus
12x squared e to the 2x. C2 to 2x plus AC2x.
That's our y prime. Now y of 0 was 1.
No.
yeah.
Yes. Y of 0 is 1. So that means when I plug in 0 for x's,
Everything goes, or a lot of stuff.
C1 plus
a lot of stuff. We have the 3/8 left.
plus
That's gonna die. Plus C1 plus C. That's gonna die. Right? Because the x is 0. So I can find the C1. So C1 is going to be 1 minus 3/8, which is 5/8. And so now y prime of 0 is equal to 0. So when I plug in 0 for x's here, that's going to leave me with 1/2, 0, 0, 2c2,
C1
0,
2C1
2c1
plus C2.
plus c2. And I know what the c1 is, so this means that 0 is equal to 1/2 plus 5/4 plus c2. This means my c2 is equal to minus 1/2 minus 5/4 plus minus 2/4 minus 5/4 minus 7. Right? And so, finally, the solution to this guy with those initial conditions. C1. Where did I put that now?
Yes, I did.
C1 is 5/8. So we have 5/8 e to the 2x plus
Negative.
minus 7/4 x e to the 2x
X squared over 4.
plus
1/4.
1/4 x squared plus b was 1/2. C was 3/8.
Plus 6.
D was 6.
X squared.
X squared equals what?
That's the answer.
Yeah, that was easy.
Yeah, you know, Staples easy button on the desk.
Can you explain how you went
Okay, you lost me on step 2.
the particular solution to that long one where you cross a bunch out?
Explain what?
Like you went from the particular.
Yeah, so I had the general form of the particular, I found the derivatives, I plugged it into the original differential equation. That gave me that huge left side. Then I started to group things because I'm going to want to set the coefficients equal. So I have to group all the x squares, all the x's, all the constants, all the e to the 2x's, all the x e to the 2x, all to the x squares e to the 2x, and then I compare both sides. right? So then the coefficients of the x squareds have to be the same because we have an equal sign. All these coefficients must be the same going all right across. And you can notice here that they're not written, but technically you have a 0x and a 0 constant, and a 0x e to the 2x, and a 0x squared e to the 2x. And so these guys are 0 anyway, but if they weren't, I would set whatever is inside the parentheses here equal to 0. But they were taken out of play automatically. So I have to set the 12 equals to this, the constant is 0, the x is 0, and the x squared is 1. So you'll get a system of equations, you can solve for the a, b, c's, and d's, then you find the c1s and c2s in the same way that we've been doing them for a long time.
Question. Is there any shortcut to allow us to take like just the characteristic equations on C1 and C2?
That will just say the characteristic equation to find C1 and C2? No. We actually need to bring the YP with us for that. Yeah.
So why do engineers do this or variation parameters? Because this is like so much more longer. So why would any engineer like do this?
I don't know. You can try the variation of parameters way. I never actually did it for this.
You wouldn't do this by hand.
Huh?
You wouldn't do this by hand.
Oh, you just plug it into a computer, so it's probably easier to compute
Yeah,
rather
yes.
than raw
You
speed.
would never do this by hand.
That's only for 4 specific cases.
Yeah.
Yeah. But maybe it uses less computing power or something. I don't know.
You remember the one on the exam when we had to do variation parameters?
That is all I wanted
This way was faster for that specific one, I think.
For
For
that one, we only have to set it up.
undetermined coefficients. There's another method that's pretty popular among the engineering crowd. It's called the annihilator method. I'm not gonna
The
cover it.
annihilator method?
It's called the annihilator.
You're not going to show us the annihilator method?
No.
Why?
It's the name, right? The other ones have such a geeky name, undetermined coefficients. Like, I don't care about coefficients. Talk about the annihilator. I don't want to.
What is what can you tell me in like 2 sentences what it is?
Huh?
Can you tell me in like 2 sentences what it is?
It's when you use differential operators to annihilate functions.
Okay.
That's very cool.
Yeah, so it's like you can think of the derivative in like if you have y double prime, if you think of d as the function called the derivative operator.
It's just like Dell.
Right? So when I apply d to some function, like dy is going to be equal to the derivative of y. Right? And if I say d squared y, it's going to be the second derivative of y, and so on and so forth. D cubed y is going to be the third derivative of y. So for example, if I have a function like f of x equals x squared, I know that d3 annihilates x squared, right? Because if I take d times x squared, this is just going to give me 2x. If I take d squared times x squared, this is going to give me 2. But if I take d cubed times x squared, that actually brings it to 0. So I need a cubic derivative operator to annihilate the x squared. So pretty much you start out with a differential equation. You're going to replace all the y primes with the d's. You're going to factor out the y's, and then you're going to think, what d function do I need to annihilate the right side, turn it into a homogeneous equation, solve it in the homogeneous place, and then, yeah, so it's called the annihilator.
Pretty cool, actually. Thank you.
Your book actually describes it, so you can go through it if you're interested, but I don't particularly care. Once again, whenever that's going to work, variation of parameters is going to work. I'm kind of partial to this. Just integrate. Come on. With all these fancy methods, so avoid integrating.
Or if you have like e to the x squared, then you might have to
Well, divided by 0.
Let's actually talk about something else. So, like I said, this course is called Methods of Differential Equations, so it's really about teaching you how to solve different kinds of differential equations, and not necessarily about the theory or about the applications, but every now and then we want to actually show you some applications. So I actually want to talk about some applications right now. I believe it is in section 3.8, where we're going to talk about mechanical vibrations.
Oh, you mean sorting?
Everyone loves mechanical vibrations. We are going to look at these from the perspective of differential equations, very sexy.
Again.
One particular kind of mechanical vibrations, more specifically, I didn't say anything. We're going to look at a spring mass system. So here is the setup. Okay, so you have some spring hanging from something. Okay. The spring has length, let's call it little L. That's the natural length of the spring. So spring hangs. So that's the first situation. Two, what you're going to do is you're going to attach a mass to the end of the spring. And let it rest. So, move this up. Attach a mass. So we have the spring, but now we attach some weight to it. So there's some mass at the end. Now this is going to stretch the spring by a little bit. Call the distance that it's this additional stretch to the spring. It's going to be big L. Now what we're going to do, because we're troublemakers, we're actually going to like do something like that. So we're going to actually stretch it a little more and let it go, or hit it at the bottom or something. That is going to start doing this at the end of the spring. So there's a mass vibrating at the end of the spring. And we want to know the position function for the mass.
Of course.
So, set the system in motion. So eventually we're going to have this thing, mass at the end of the spring, it's going to be vibrating. So we already have the length L, which maybe was here, the length L here when everything was nice and at rest, and then there's an additional distance here, which we're going to call U of T. So there's a little bouncing up and down happening here at the end of the spring. I want to actually measure that motion. So, how do we go about doing that? Well, so now, the setup. Let's start with preliminaries. Things that we need to know, remember, background information. Let's start with the first one. Newton's second law. What's Newton's second law say?
F is ma. The vector.
Force equals mass times acceleration. Which means if you have a mass being accelerated by a force, you want to find out what is the magnitude of the force accelerating this mass. Take the mass, multiply it by the acceleration, and that will tell you how strong a force is pushing the object. This is Newton's second law. So what this is saying is that if I say F of T is the force experienced by the spring system, can somehow think of this as the mass times the acceleration. But what is going to be the acceleration?
The second derivative of u of t.
Exactly. So the acceleration of the object is going to be given by u double prime. So that's from Calc 1. So now you start to see the second order forming. Right, acceleration is going to be the biggest thing. Otherwise, we're going to have velocity and position to worry about. Those are going to give us the lowest derivatives. But how do those come in? We also have another thing that you need to know about. So Newton's second law should know. Hooke's law you should know, because it is a spring after all.
F is kx.
So let's say F sub S is the force exerted by the spring itself. What does that mean?
Negative.
Right.
Absolute value
Negative
of x?
Or what?
Isn't it negative k absolute value of x?
Well, technically the K we always think of as the positive. But no, here we're going to look at X, where force exerted by spring K is what we call the spring constant. It is considered positive, and it is a property of the spring itself, so it depends on how big the spring is, how strong the spring is, what material it comes from, property of the spring itself. And X is the distance the spring is stretched or compressed under this force. Under Fs beyond its natural length. So the little l is not included in this distance beyond natural length.
So does that mean
Experience.
does that mean the spring cannot the mass cannot oscillate so that if it would go below, it'd be like L minus some distance, because it like go all
Yeah, it could be, it's the little l plus or minus some distance, because it can actually get short. Now, it's negative because we're going to have this weird convention here. Convention down is the positive direction. Yes. Normally, I know we think of up as a positive direction for this set of equations. We're going to consider down as a positive direction, so we're going to throw in negative signs every now and then to think of it in the opposite way. So we have that. Now, there is another force that we have to worry about. There is something called 3, known as a damping force. So, very common damping force example is air resistance. This is a force that goes against motion. Force that resists motion. Yeah, some sort of friction. Usually we talk about it like in the fluid. Friction would be a damping force. But this, we think of it as like air resistance, or if the spring system is in some sort of fluid, the resistance given by the fluid. Here also, we make an assumption, just to simplify things. It seems to work out at the end.
It doesn't exist.
This force is proportional to the velocity of mass, right? So it's kind of like if you're just walking, you don't really feel any air resistance. You start running, you feel the air more. The air kind of resists you more. You're hitting more air particles. The faster you are moving, the more the fluid that you're moving in is going to resist you. And we make the assumption that it will do so in a proportional manner, which means I can think of the damping force, which I'm going to call F sub D. There's going to be some constant, which customarily is gamma. We have the minus sign because we're thinking of the opposite direction of what we normally think of. And this is going to be U times prime. So it's proportional to the velocity, but it moves in the opposite direction of the velocity. And the gamma here is called the damping coefficient. So it's just a measure of how much the fluid is resisting motion under this velocity, at this velocity. Okay, so that's something else that's going on. So the force is experiencing, the spring mass system is experiencing all sorts of forces. One is Hooke's law, the spring itself is exerting a force. The spring hanging under its own weight is going to, the spring under the weight of our disturbance is going to be going with a force, as well as in the equilibrium situation. So this means when I attach the mass to the end of the spring and I just let it hang, no one's bothering it, and it actually comes to rest and it's just there, not in motion. We call that position equilibrium. So this means at rest.
Oh, so it's like the homogeneous case.
Not really. I'd rather you think of it as a kind of initial condition.
Okay.
So now once it's at rest, there are a couple of forces that are going to act on this mass. For one, its weight is pulling it down, which is going to be mass times gravity, right? So that's going to be the weight. But of course, the spring itself is going to resist this because of Newton's third law. Every force has an equal and opposite reaction, okay? So the fact that this thing doesn't snap means that the spring is providing just enough force upwards to resist the weight hanging downwards. So this means it's Fs. Now, by our diagram previously, remember the length that we extend beyond the natural length was big L plus U? So this is going to just be minus K times big L plus U. And that would be the free body diagram in the equilibrium situation. So the weight is hanging, the spring is what's keeping it up, its weight is pulling it down. The force that the spring is pushing up is going to be this guy, and the force that the spring is pushing down is going to be that guy. Well, in the equilibrium, it's just L actually. So ultimately, what does this mean? If the downward force is mg, the upward force is minus kl, and it's not moving because it's at equilibrium, sum of all forces must equal 0. So the mg plus the fs must equal 0. So this means that mg minus k minus kl must equal to 0. We're going to use that later, so remember that. Call that star. Okay. Any other facts? Newton's second law tells us that must be a function governing u in terms of forces acting on u. Hooke's law tells us about that. The damping idea tells us about that. And at equilibrium we have this.
What's our assumption for gravity?
Oh, gravity is going to be, g is going to be, remember down is a positive direction, so it's positive 9.8 meters per second squared, or positive 32 feet per second squared.
Are we going to be considering springs on like a horizontal frictionless table?
No, just the hanging spring. That's okay. Let's actually put this all together. we'll look at the forces on the system in two ways. So, all the forces acting on the system under its vibrating motion is going to be given by this. So this is going to be the sum of forces acting on the vibrating system. Now, we are going to say what those forces actually equal to by all the considerations we've made. That is going to be 1, well, the weight of the mass, plus the force exerted by the spring, plus whatever resistance force it's experiencing from the environment, so the damping force, plus just in case we want to give more trouble and actually have some external force acting on the system.
This would be like
So
some.
maybe attach an engine, or every 10 seconds we do this, and there's just a force that comes by every 10 seconds and does okay, just to mess with it, right? So a lot of times we're going to assume there's no external force, in which case you'll make this 0. But ultimately, what this ends up becoming is going to be, well, this will be m times u double prime equals m times g. Now, Fs, remember, this is under the vibrating system, so the length for the spring constant here is going to be L plus U, because the distance is actually changing. Fd, well, this is going to be minus gamma times U prime plus T. And what you realize is that here, this is going to be m times g minus k times L minus k times u minus gamma times u prime plus f t.
What is that equilibrium?
We know that this expression here must be 0 by star.
No, I mean because of the negative KL plus U.
Well, this equation currently is not measuring equilibrium. But because of the equilibrium situation, we know that this expression must be 0. So ultimately, finally, bringing all the u's to one side. M u double prime. I'm going to add the gamma u. I'm going to add the ku. And on that side, there's just going to be the F15. I want you to notice that this is a second order linear differential equation with constant coefficients, because that's the mass, that's going to be the proportion for damping, that K is going to be the spring constant. And it's non-homogeneous if the external force is non-zero. So sometimes we just set it in motion at the beginning and then we just leave it alone, in which case we say there's no external force. So there was one just at the very first instance. But other than that, we will make it 0. But if there is some sort of external force that the system is experiencing, we'll just express it in some other function. So,
Would this be in perpetual motion, or would it stop at some time t?
that is a good question, but we are going to actually figure that out by solving problems. Because it's a differential equation, it has a solution, so its solution is going to tell us what's going to happen in the long term, at least theoretically. Okay, so that was the derivation.
Oh, because of air resistance
Air
of this. Oh, yeah.
Yeah, but your external force is on the other side. Yeah, that's true. If it's continuing to.
Okay, things to keep in mind here. So these problems here are going to be, again, word problems. So I just want to make sure that you have some things that you want to pay attention to. 1, the mass is equal to the weight over gravity. That's one way you can find the mass. Weight is a force, it's equal to mass times gravity, which means if you're given things like units in pounds, you can use this equation to find the mass. If you're given something in grams or kilograms, it's already in mass form, you don't need to change it. Something else. You can often find the spring constant by the weight over L. So this is the length that the mass stretches the spring without anyone messing with it. Length, mass, stretches spring. So that's how you'd find that guy. Gamma, this is the damping coefficient, how you're going to find it. Remember, the velocity times gamma is going to give us the resistance force, so you can think of this as the resistance force over the velocity. So sometimes the problem might say, oh, there is a resistance force of 2 pounds when the mass is traveling at 4 meters per second or whatever. You're going to take the 2 divided by 4 meters per second, and that will give you the gamma coefficient. Make your units consistent. That's something that can actually happen. So if things are measured in inches and you know you're using your gravity in feet, change everything to feet. If you need to apply gravity, just
Make it consistent.
That's right.
Make it consistent.
Make your consistent. They must match
And you want to know what it is in feet per second.
G.
32. Yeah, I keep forgetting. Because it's, I remember 9.8 is so much easier. Or 10.
So technically knowing how to solve those is just you knowing how to set up second order differential equations and then solving that, which we will get to next time. And here are the examples we'll do next time. So you can look them up. Look them over for next class.
One of them is
Yes.
Meters and feet.
It depends on the problem. So the kind of problems that you'll see are like these. So there are some other problems here, but the ones that I marked with asterisks are the ones that we'll be covering for this section. So pass these around.
So are the non-asterisk ones you don't expect us to know?
Come again?
The non-asterisk ones you don't expect us to know?
The non-what?
The non-asterisk one you don't expect us to know?
Well, not right now. They're completely different topics.
Oh.
Did you say pounds was a weight?
Pounds is a weight, which is a force.
Oh.
We're using pounds as a force.
And kilograms is a weight?
Mass, yeah.
Kilograms is mass,
It's
yes.
good quality.
Does that mean British people, they weigh themselves in a mass? And
So
we
next
weigh
time we'll get
ourselves in
through
a
these.
weight?
They weigh themselves in
And
pounds,
we'll wrap it
but
up.
that's mass.
We'll wrap up there for
But
now.
when we say pounds, we mean pound force.
Pound force,
Yeah.
the force.
You can look over something. You can say,
Like, does that mean like they actually, their weight would be in units?
No.
Like,
It
if they,
counts, but it's not units. Because that's count force. It's the same thing, but it's
So wait, no, this would answer it. What is the mass to that?